2, 1, and away we go. Alright, so welcome to the first pre-recorded lecture. Perhaps there will be more in the future, we'll see. Right, like I said, got some hectic family things going on right now, so... Alright, but let's get to it. So, what's the goal? So today, we will finish up the slides for linear transforms. So, that's very exciting. Alright, so what's sort of our last goal? Well, we set it up last time. Our last goal here is to prove something called the rank nullity theorem. And we kind of got into it. We didn't finish it. We sort of took care of the trivial cases, and then we kind of set up what like the main proof is. But before we get there and get to that, let's remind ourselves of what exactly is going on and kind of start revealing kind of why we're doing this. Right. Okay, so given any matrix, here it is, we can define a couple of things. So the null space, which is the set of vectors so that a times x is equal to 0, and the column space, which is the set of vectors so that y is equal to an a times x for some x. So the x we don't care about, we care about the y. Alright, so note a few things about these things. Look where they live. The null space is a subset of Rn, and the column space is a subset of Rm. Okay, right, so the column space are things that can equal a matrix multiplication. So since this is an m by n and this is an n vector, this product would have to live in Rm. Right, and similarly with the null space, right, these are the x's so that a times x is equal to 0, and the only x that would make sense is something living in Rn. So that's where these subspaces live. Indeed, they are subspaces, hence their name, which is nice. And so specifically, they can also be thought of as the kernel of the linear transform induced by matrix multiplication, that's the null space, and the range of the linear transform induced by matrix multiplication, and that is what the column space is equal to. All right, cool. So these are usually referred to as like the fundamental subspaces of a matrix. As I mentioned, two others usually get thrown in, but they're just the null space and the column space of the transpose of the matrix. Why transpose will make sense later on. But for right now, we'll just focus on the null space and the column space. We'll bring in how does transpose surprisingly show up and play a role in all of this stuff later, when we really get into the nitty-gritty of using all of this fun stuff to solve systems of linear equations. Because again, that is our big overall goal. And so all of the stuff that we've been doing with linear mappings is really just setting the stage to sort of, knock that one out of the park. This could be great. It's going to be great. Alright, so that's the null space and the column space. So the null space pretty much is just this, right? So you can think of it as a times x equaling 0. Also, keep in mind, this is the solution set to a homogeneous system of linear equations. So again, this will come back around. It's going to be great. And the column space, on the other hand, right, well, the null space is pretty much this, or also the kernel of linear transform. The column space is another way of thinking about it. It is the span of the columns of the matrix, hence the name, right? So null space makes sense as a name because it's, we have things getting mapped to 0, null, okay, gotcha. Column space at first glance is like, why? Why is that called column space? Right, sometimes in math things get names and you're just like, sure. But for the most part, the names are usually meaningful, right? So column space, the span of the columns. Things do fall apart when you name things after people, because then it kind of obscures what you're talking about. Like I could say, oh, the Weierstrass theorem, and it's like, oh, yeah, sure. And there's also a problem with that too, because Weierstrass was a very famous mathematician, so there's a bunch of stuff with his name on it, and so it's like, which one are you talking about? Normally, you're talking about every continuous function is approximable by polynomials, but, which is a mouthful, so that's why you just say, the Weierstrass theorem. Oh, okay. But anyway. Alright, so last time we indeed proved that the column space is precisely the span of the columns, so the name is legit, right? And again, the reasoning for that is matrix multiplication of a matrix times a vector can be thought of as a linear combination of the columns, so boom, the proof just falls out of that idea. Cool. All right. So the main thing about not the main thing, one of the main things that we care about when it comes to the column space and the null space are their dimensions. So the column space lives in Rm, so it's a finite dimensional vector space. And its dimension is called the rank of the matrix. Yay! Right. So, kind of interestingly, even though the column space is a subset of Rm, it is also bound in dimension by n, right? So the rank never exceeds m or n. It's always less than or equal to the smaller of the two. Right, so since it is a subset of Rm, it's automatically got dimension less than m. It's a subset of it's a subspace of Rm. Its dimension cannot exceed m. That's where it lives. But it's also bounded by n because the column space is the span of the columns, of which there are n of them. And so by Steinitz exchange, we know that the number of elements in any basis for the column space, right, cannot exceed n. Right, this is a collection of linearly independent things. And by Steinitz exchange, we know that if you're in a set that's been spanned by n things, you cannot have more than n linearly independent things living in that set. So the rank must be less than or equal to n as well. So it's less than both of them, so it's less than their minimum. Cool. And this is actually, while this is kind of easy to verify, this is a surprisingly, restrictive bound. And when we get into using all this stuff to solve systems linear equations, so when your rows and columns are unequal, this seemingly innocuous inequality becomes incredibly powerful. More on that when we get there. This is we are getting a little to the point of when are we getting to the fireworks factory? But we are getting there, trust me, and it's going to be great. And again, I'm assuming if you don't know what I'm talking about, I'm referencing an episode of The Simpsons, which that's the more I think about that, the weirder that becomes. Where I'm referring to an episode from 30 years ago, and yeah, I think that's definitely my age showing now. Yeah, there's 40 seasons of that show or something, and I don't know, I only know the first 10 basically. I'm completely ignorant to the majority of that show's existence. It's crazy to think about, but anyway. Okay, so equipped with the idea of rank, we can then verify a couple of things about rank. Now we've defined it, let's investigate it. All right, so a couple of neat things is that rank is basically never equal to 0. The only time the rank is ever 0 is if the matrix you're working with is nothing but zeros. So, right, for the most part, we will work with matrices that are not equal to 0, so our rank is always guaranteed to be at least 1. So that's cool. And here we see that the rank can only line up with the number of rows if the linear mapping induced by matrix multiplication is in fact an onto one. That's really nice that we have that now. So remember, we care about onto and one-to-one for linear mappings because a one-to-one and onto linear mapping would be an isomorphism. So that would mean that the matrix multiplication we have is classifying the vector space, right? It's completely encoding all of the information. Quite interesting. But right. Okay, and so, right, we worked out the details of this proof. So the rank equaling 0 getting us the matrix is equal to 0. So again, anytime we're ever proving a matrix is equal to another matrix, our go-to trick will always be to multiply by standard basis elements. Yeah, it's just a nice trick, and it always works out really well. Yeah. Okay. And then this one is basically for free because the rank equaling m would mean that the dimension of the range of the linear mapping induced by matrix multiplication would equal m, which means it would equal the dimension of the codomain, which we proved is equivalent to the mapping being onto. So this is just a reformulation of something we already proved, which is always a good thing. And that was actually a joke in grad school that we had, where it's you want to get your name on a theorem, it's just to repurpose something else, and that's how I'm gonna get my name on something. I'm just gonna, this is equivalent to this thing that's known, but this is more useful, so, or something like that. My buddy Jay, that was his goal, and actually, specifically, Actually, problem number 2 that you're doing in problem number 5, one of my favorite problems. I forget what class. I think it was in functional analysis with him, and he was like, because the first case you need to take care of where the kernel is equal to the whole space. That's like that's really the trickiest part. Like once you get around that, then if you follow your nodes, it comes out nice. But yeah, that was his he wanted to claim that as his theorem. It's like if the kernel, that part he's like that part isn't outright stated. You always state the thing. But he was like, man, if the kernel's equal that, then the function's 0. That's my theorem. Anyway. Okay. All right. So if the dimension of the column space in your matrix is useful, then the dimension of its null space stands to be useful. This is called the nullity. I'm not going to give it a fancy proprietary symbol. I'll just call it dim null. Rank is a shorter word, so it's good for an operator. Nullity, right? We're already using NUL for the null space. I don't want to use NULL for the nullity of the that could be confusing. So I'll just say dimension of the null space. All right. So where we saw the dimension of the rank tell us something about the mapping being onto, here we see the dimension of the null space telling me something about the mapping being 1 to 1. So as I mentioned, for the most part, when it comes to linear mappings, what you really care about is 1 to 1, and this is why, basically. So here we see the linear mapping being induced by matrix multiplication, 1 to 1 precisely when the columns are distinct and linearly independent. So this is a serious enforcing of assumptions, right? This is really requiring the matrix that you have to be very well behaved. So this is why 1 to 1 usually we care a lot more about than onto. And as we're eventually going to prove at the end of today, when the dimensions are equal, then 1 to 1 and onto are the same thing. All right. Okay, yeah, and so the proof of this is not too bad. And again, we did this. The dimension of the null space is 0, means the null space is trivial. And hey, set up your linear combo. Hey, linear combo of columns, that's the same thing as matrix multiplication. And there you go. The only thing in the null space is 0, so all of the scalars must be 0. And so our set is both distinct and linearly independent. So again, remember, proving that something is linearly independent, you don't need to get all hung up about the distinctness, because you will usually get that for free from just setting up the scalars. Now, using the fact that it's linearly independent, you need the distinctness, right? And that's coming right here. So, right, obviously we want all of these things to equal 0. And if I don't enforce distinctness, if I just say the columns are linearly independent, right, well, the sets, right, when you write a set like this, right, it could be that this is linearly independent, but there is repetition, because as a set, the set doesn't care about repetition. The set will just consider that one element, even though it appears multiple times. Right, right. A set does that. If you've been getting confused about this or being cranky about it, it's like, well, but you listed it, so right. If they repeat, then you don't have the linear independence. It's not exactly true, all right? Because a set like this, if there's a repetition, the set collapses it down, right? The set doesn't care if it showed up multiple times; it only cares if it's in there, right? A set, we only care if you're in or you're out. We don't care how many times you have a representation. The things where you care about that are called multi-sets. And that's a completely different can of worms. So if that's been, I kind of just realized that, where I'm like, oh yeah, I don't think I pointed out that when you write a list like this, you're not enforcing distinctness by default. You have to include that you're doing that. Okay. Anyway, so the hypothesis then that we have distinct and linearly independent, since we don't have any repetition here, and we have linear independence, it's got to be that these scalars are all equal to 0, which means that x is equal to y, and the proof is done there. Yay. And then, of course, for closing the loop, being 1 to 1, the null space is the kernel of the linear transform, and 1 to 1 of a linear mapping means the kernel is trivial, so that's a fun, just get that for free. Okay. All right, and then we looked at the extreme cases of rank nullity, basically going if the dimension of the null space is as small as it can be. So again, the null space is a subset of Rn. If it's as small as it can be, then the rank has to actually equal the number of columns. And likewise, if the null space is as large as it can be, again, because it's a subspace of Rn, then the rank is equal to 0. So this tells us that when the nullity is as small as possible, or when it's as big as possible, we've got some stuff we can conclude about the rank. Right, and this is, again, super easy, right? Because if the null space is 0, we just prove that means the columns are distinct and linearly independent. The column space is spanned by those things, and since that is a distinct and linearly independent set, that means that this actually forms a basis for the column space. It will always span the column space, but if we don't know these are distinct or linearly independent, we cannot conclude this. All right, cool. And the dimension of the null space equaling n means that the null space is all of Rn. So my matrix maps everything to 0, and the only way it could do that is if it was actually equal to 0. Right, and again, doing our favorite multiply by the standard basis elements trick. Okay. All right, and now, okay, back up to speed. And it only took me 16 minutes. Great. Yeah, the rank nullity theorem. Here it is. Right, so like I said, in my opinion, which is the correct one, this is the most important theorem I think we're going to prove. There's probably some other things we'll prove along the way that somebody might consider more broaderly important, but for the story we're telling, that right, we want to solve linear systems of equations, this right here is the most important thing. This completely and utterly dictates how systems of linear equations behave. Everything about them is basically built off of this, which is really surprising, and it becomes really clear, of course, once we get there and start applying it. For right now, this is an incredibly surprising result, though, if you really just break down what it's saying. The number of columns of your matrix, I don't care what the rows are, the number of columns dictates something about the subspaces created by the matrix. The number of columns tells you something about subspaces that the matrix creates. The number of rows plays no part in that. Right, that's really bizarre. But it's not super bizarre if you think about, right, the subspaces we're talking about are generated by the linear mapping induced by matrix multiplication, and this is an m by n matrix, so the multiplications that we can do are using elements of Rn. So it's not too surprising then that, right, the domain of that linear mapping plays a huge role here in terms of how the subspaces work. What is a bit more surprising is that their summation of these two subspaces is equal to n, considering, again, that the rank here is the dimension of the column space, and the column space is a subspace of Rm. So, right, the fact that a subspace of Rm, where m could be humongous, m could be way bigger than n, but here we see that the dimension of the subspace generated by the matrix there is it's bounded above by n, right? This is always greater than or equal to 0, so this can never exceed n. That's interesting. All right, cool. Okay, so yeah, this is a very striking theorem, right? It seems like you shouldn't be able to get away with something like this. So it's, to me, that's why it ends up being such a fundamental theorem. It's like very surprising conclusion, and the applications of this are like fundamental to what we're trying to do. So that's why I would consider this the most important theorem. I don't have like a face cam or anything on, but of course I'm sitting right next to the goddamn textbook of the course, and if Jim Heffron ever sees this video, I want you to know that how dare you not give this its appropriate name. It's just like I found it and I was pissed because he just like called it Theorem 2.14 or something. And like now I can't find it, so I don't know. Maybe actually go. Well, no, because I remember I looked in the index, I didn't see the words rank nullity, and I was like, oh, he done goofed. But anyway, all right, cool. All right, so let's actually prove this now. So the first thing we'll note is that by the previous results, we've taken care of two extreme cases that we don't need to worry about. If the dimension of the null space is equal to 0, then we know the rank is equal to n, as we just proved, so the summation works. So we're done. Okay, and then likewise, if the dimension of the null space is n, then we know that the rank must be 0, so again, they sum up to n, and we're done. So, what we can go ahead and do is assume that the dimension of the null space is some number strictly between 0 and n. So in other words, it's a non-negative integer that's no bigger than n minus 1. Like this. All right, so let p equal that. All right, so the trick then here is as follows. Take any basis for the null space. All right. Okay. This has to have p elements in it because, right, we said that's what the dimension is. Now, p is not equal to n. Okay, so what I have here is not a basis for Rn. It's a linearly independent subset of Rn, and we know that any linearly independent set can be extended to a basis. So that means I can add some more vectors here, right? Note p plus 1 is no more than n. It's very possible that, like, p plus 1 is n. That can happen. Like, you're just missing one vector. Which, conveniently, the example we did way back and a couple slides ago was exactly that. So what we did. Not yesterday. I think on Tuesday at the end of the day we did that. But anyway, previous slides have this. All right, so yes, this can be extended. So there are things that can be added to this that make it a basis for Rn, and now sort of the picture becomes super clear. We have, hey, the dimension of the null space, that's the number of vectors here. We have p of them. We have extended to a basis for Rn, and hey, that means I've got n elements. Hey, p minus n, n minus p then, which of course is the number of elements we have right here. If we could prove that was, oh, I don't know, equal to the rank, then we'd be done. Because then you could just add this over and we'd be done. So, yes, that is the plan. So we will verify that this indeed forms a distinct set, and it is a basis for the column space, so that guarantees that the dimension of the column space is equal to the number of things we have here, which is n minus p. Right, so we have n things, and then if you take away p, you get these ones. So this is n minus p things in it. Okay. All right. So something I want to point out is, so here I'm saying fix a basis for that. Note that this would have to be distinct, right? So by basis, we mean it's linearly independent and it spans. There are, right, this cannot have less than p things in it then. If it did, that means the dimension is less than p, which can't happen. Same thing for this. Right, this must be a distinct list. I didn't explicitly include that. I think I explicitly noted that too. If you've got a list and you're told it's a basis, it's automatically, and if the list has the right number of things, then it's automatically distinct. So that just caught my eye that I didn't include that. It's subsumed there. Okay. Yeah. All right, so that's all we got to do, that this is in fact distinct in a basis for the column space, and that will complete the proof. All right, so again, not too bad. So how do we do that then? Okay, so, all right, well, we want it's distinct in a basis, so in other words, we need to verify it's distinct, linearly independent, and it spans. Okay, so distinct and linearly independent, we can knock out of the park in one move by just setting up the linear combo and verifying that all the scalars are equal to 0. So let's go ahead and do that. All right, so let's make the trivial linear combination. Hey, I can factor a out of this whole thing. That's very nice. And now what do we have? We've got a times this stuff is equal to 0. Well, that would mean this stuff is in the null space. Right, so you've got this linear combination, lives in the null space, and the null space, we know, spans these vectors. And now, hopefully, you immediately see that we cannot have non-zero scalars here. If one of these scalars was non-zero, okay, well then this linear combo is equal to, is in the span here, so this linear combo is a linear combo of v1 to vp. If one of these scalars is non-zero, isolate it, move everything else to the right, and then you get that this is a linear combination of vectors coming out of this set, but not equal to itself, right? Because you have it on the left-hand side, you don't have it on the right. and that is no good, right? This is a linearly independent set. So, right, if this was in the span here, that would mean that I could set up the... So I'm tripping over my words here. Right, so if this was in the span here, that means we can write 0 as a linear combination, but this vector would have a non-zero scalar, right? Specifically, it would have 1 attached to it. Right, so this is in the span here, it's a linear combo of everything but itself. Move everything else over, then you get a linear combo equaling 0, but you've got non-zero scalars. So that contradicts the linear independence, and so it's got to be that all the scalars are in fact equal to 0. Thus completing the proof of, the distinctness and linear independence of these vectors right here. Okay, cool. All right, so consequently it's distinct and linearly independent, so the only thing we need to verify now is that this indeed spans the column space. Okay, so the first thing to note is that, yeah, it's a subset of the column space, so the span is contained in the column space. This is a subspace. Span is the smallest subspace, so we have to have that subset. So now we just need to verify that anything in the column space is actually a linear combo of those things. So take something in the column space. If you're in the column space, that means you're a linear combo of something out of Rn. Remember, the V's are chosen to be a basis, so that means there is some linear combo that equals x. Now, if we look at A times x, remember, matrix multiplication means that you can rewrite it as a linear combo of, so matrix multiplication is linear. So when I do A times x, this distributes, it pulls apart the way you want it to. But note, V1 to Vp all belong to the null space. So A times those things are equal to 0. So you just pick up a bunch of zeros there, and all the leftover stuff, hey, that is precisely these things right here. So that means y lives in the span of those vectors, and that completes the proof. We then know that this set right here indeed is a basis for the column space, which means the dimension of the column space is n minus p. So the rank is n minus p. P is the dimension of the null space, so adding rank and nullity gives you the number of columns. And the proof's over. Nice. All right, cool. So there we go. We've proven the rank nullity theorem. And not too bad of a proof, and kind of a clever idea, honestly. This idea of taking the basis for the null space and then extending it. It's a slick little move. So it's worth noting that, right, this is how I'm presenting the proof. There are a few other ways of proving the rank nullity theorem. If you go to the wiki for it, you'll see there's a couple of ways of handling it. My favorite way of proving it is not the way that we did it here. The way I remember proving it, because we used a different textbook when I took this class. The way I learned how to prove it is this like insane argument. Not an insane argument. There's a way of doing it with. So somebody actually asked us if we were going to talk about left or right inverses in this class, and I'm like, nah, we're not really going to. I think I'll briefly mention it. But there's a way of proving this using left and right inverses. Because you can prove it's really like wacky how you pull it off. It's it's really neat. That proof's really crazy. So there are other proofs of the rank nullity theorem that are more that proof especially is like crazy like algebra, like more general algebra than linear algebra. It's more based on is it right? It's a right inverse of an additive mapping induces a direct sum in the domain, and then from there, like right LA pops out of that for free, basically. But like proving that and like the other things you need to prove are like really, it's way more involved than like you want it to be, basically. But Yeah, it's a slick proof. I like that one. So if you're interested, I can send that one to you. I think the wiki point talks about it, but this is pretty standard proof of the rank nullity theorem, where you set up the basis for the null space, extend it to a basis of Rn, and then the things you added to extend it, that gives you the basis for the column space. So that's pretty good. Okay, cool. All right. Okay, so now we've actually proven the rank nullity theorem, and I've been making a huge deal about it as the most important theorem. Okay, well, can I give some credence to that? Can I give some results that kind of justify that sort of bold claim? All right, well, I can kind of give you one right now. Again, this will all play a huge role when we get into solving systems, which is our next task, so we'll immediately see this in action. But yeah, so a matrix is said to have a full rank if its rank is equal to n. Now note, rank is bounded above by n, right? Remember, the rank is less than or equal to both the number of columns and the number of rows. So it's bounded above by m and n. And so full rank, though, will be if the rank is actually equal to n, right? So in other words, the rank is equal to the number of columns, and this can only ever happen if the columns are distinct and linearly independent. So hey, we've already seen that show up, right? That was equivalent to the null space equaling, the dimension of the null space equaling 0. And also the linear mapping induced by matrix multiplication being 1 to 1. And so again, like I've noted, we care a lot more about the linear mappings being 1 to 1 than we do them being onto. And here's another theorem in that direction. Okay, so let's prove this. And the good news is, this is simply rank nullity in disguise, right? Suppose you have full rank. By the rank nullity theorem, we know that n is equal to the rank plus the nullity, but the rank is n by hypothesis, so you subtract these over, that gives you the dimension of the null space of 0, which we proved is the same thing as the columns being distinct and linearly independent. Hooray! Full rank giving you columns are distinct and linearly independent. All right, that's it. Forward direction's done. Nice. And reverse direction is also immediately from this as well, because we proved that the columns being distinct and linearly independent is the same thing as the dimension of the null space equaling 0. So, hey, if you know that's equal to 0, by rank and nullity, rank must equal n, right? In fact, we actually proved that as an extreme case, that the dimension of the null space being 0 gives you the rank is equal to n. So, don't need to explicitly get to the theorem, but there we go. Cool. Nice. So there we go. This will end up being a huge result for us once we get back to solving systems. Having full rank is basically what you want, because it guarantees that your system of linear equations is going to have a unique solution. So it's kind of what we want. So there we go. All right, beautiful. So that's very nice. All right, cool. So there's some nice, quick justification for kind of why we care about rank nullity. It gives us this really neat little result here. So we're pretty happy about that. All right. So what next? So, right, we're not jumping over to systems just yet. Right, we still got some more slides to do. But our main task before we jump out of here and get back to systems and start hacking away at that stuff is to, of course, prove the rank nullity theorem for vector spaces. Okay, right. So we proved it for matrices, which are the linear mappings from Rn to Rm. But we would like to do this for general vector spaces, or at least it'd be interesting to see if there was a result for general vector spaces. And in fact, there is, and note something. The codomain does not need to be known to be finite dimensional. So this actually is a little bit stronger than what we proved at first here. But it's not, hopefully, too surprising that we can get away with this. If V is finite dimensional and T is linear, the range has to be finite dimensional. It doesn't all of a sudden become infinite dimensional, right? So remember, the span, the image of a span is the span of the image under a linear mapping, so that would automatically guarantee that this is finite dimensional. So yeah, the Wrinkly Theorem does in fact hold for vector spaces, and we can actually have some lax assumptions on W. We don't need W to be finite dimensional, so that's kind of nice. Okay. But right, again, dimension of the kernel, right, this is, again, the same thing as the nullity for a matrix. This is the range, so, yeah, it's the rank nullity theorem. Again, but written more arbitrarily for any vector spaces you want. And again, W can be chosen to be a little bit more interesting. All right, so yeah, so we'll prove this, and basically the proof of this is going to be, well, we got rank nullity for matrices. Every linear mapping between finite dimensional spaces is a matrix multiplication in disguise, so we just basically have to retrofit everything to just, so we can apply the original theorem and just get this. All right, and then, hey, yeah, right, and recall that if you've got n and m, where n is an n-dimensional vector space, or v is an n-dimensional vector space, and w is an m-dimensional one, then, right, any linear transform from v to w, we can find a matrix that represents the linear mapping. So basically what we would need to do then is, okay, we want v here to be n-dimensional, which first we'd have to take care of the trivial case of zero-dimensional. And then once we get there, we have this. And then, hey, the range we want to be m-dimensional, which we know it's going to be finite dimensional, so we can take care of the trivial case there. And then we can finally just set this up and then apply rank nullity and be done. Great, so that is the plan. So we've planned the work. Now let's work the plan. To facilitate things, this setup right here will just be announced as let A be the matrix for this linear mapping with respect to those bases. Yeah, rather than writing out all of this, we can just one sentence explain what's going on, right? A is the matrix for this linear transform. Okay. Okay, so, right, the plan is to basically use this fact to prove this, but, right, we and then just apply rank nullity with respect to this matrix that would complete the proof. But, right, we gotta, right, so, again, these are arbitrary vector spaces. They could, who cares what they are? But we know that they're going to be isomorphic to things we like. So there's a little bit of work that needs to be done to sort of explain how we can carry over everything about this over to here. So we got a few results we got to prove, and so they're not too bad. So let's see, you've got the matrix for a linear transform respective bases B and H. So here again, V is finite dimensional, and W is so V is n-dimensional. W is m-dimensional, B is a basis for V, and H is a basis for W. So what we want to verify now is that the null space of this matrix is the kernel of this linear transform after it's been coordinate transformed. So, right, remember the normal way we define null space was that it's the kernel of T, where T is the linear mapping induced by matrix multiplication. And that's only good when V is Rn, right? If V is some generic vector space, then we got to feed it into a coordinate transform, and conveniently it lines up. So that's nice. So we've got that. All right, and then similarly here for that. All right, so if we are the null space of A, that means that A times X is equal to 0. Now define V as an element of V to be the linear combination of its basis elements where we scale by the entries of X. Right, and note that that would mean that the coordinate vector for V would actually equal X. Right, because again, the coordinate vector is just what are the scalars you use to make the linear combo. All right, and because of that, since A represents T as multiplication, and we know this is equal to X, that gives me that T of V's H coordinate representation is equal to 0, and the only way that can happen, because the coordinate transformation is a linear isomorphism, it's the isomorphism explaining how W is the same thing as Rm. It's got to be that the thing on the inside is actually equal to the 0 element of W, and thus V would be in the kernel for T. And note that that means that the coordinate transform of V lives in the coordinate transform of the kernel, and X was chosen to be, and we rigged V so that it was equal to X in terms of a coordinate transform. Right. Cool. Right. So yeah, there's a lot of ins and outs and what have you about this proof and what's going on here, but the basic gist of it is, right, things in the null space here are A times X equaling 0. That X can be represented in V as a linear combination, and since A is the matrix representation, multiplying by its coordinate gives you A times X, that gives me 0. And then that gives me that this thing in here has to be 0, so V must be in the kernel, and then feeding it into the coordinate transform then gets me that X is in the image of the coordinate transform of the kernel. Right. A lot of hoops to jump through. None of them are too bad, but they're a lot of hoops, so it's a lot to keep track of. All right. So we got the forward subset, so we proved that the null space is a subset of this, so now we want to prove this is a subset of the null space. So take something in this set, that means it is equal to V's coordinate vector with respect to B for some V that's in the kernel. Since A represents the mapping T as matrix multiplication, right, since you're in the kernel, that means T of V is equal to the 0 element. The coordinate representation of that with respect to H must be 0, because, again, this is a linear mapping, this coordinate transformation. Okay, now A is the matrix representation of T, so we get this nice multiplication, and that means, hey, this thing right here, which is what X is equal to, we've got A times X then is equal to 0, so X is in the null space, and we get subset in the other direction, so the proof's done. All right, keep going. Let's let Y be in the column space of A. All right, we want to prove then that Y lives in the range of T after we coordinate transform it. Okay, so if Y is in the column space, it means Y is equal to A times X for some X out of Rn. So pull the same trick, let V be the linear combo of the elements B, which are a basis for V. The coordinate vector for V then is X, so by matrix multiplication we have this, and then, hey, look, Y is then equal to a coordinate transform of the coordinate representation of T of V. T of V lives in its range, so that means Y, which is equal to that, would live in the range of T after it's been pushed through the coordinate transformation. Because again, Y is an element of Rm, T of V is a subset of W, and this is the transformation that turns these elements of W into elements of Rm. Okay, cool. All right, so we have subset now in one direction. The column space is contained in the range of the linear mapping after it's been coordinate transformed. So go the other way, take something that's in the range, post-coordinate transformation. That means that there is something in the range so that Y is equal to that. All right. Since W is in T of V, that means there is a V it's equal to. And thus, since Y is equal to the coordinate vector for W, that means it's equal to the coordinate vector for T of V. A represents T of V in terms of matrix multiplication, and this thing must live in the column space because it's something times A. That means Y then must be in the column space of A. So, hooray! Not too bad. So again, yeah, none of this is bad, but it is, you got to keep track of what's going on. So right. So like I said, there are a bunch of hoops you need to be jumping through, right? Because we're taking elements of arbitrary vector spaces and then pushing them over into Rm. So right, it's not too horrible, but there is a lot to be keeping track of, right? This is a subset of Rm. If you're in it, that means there's something in the set that you're equal to. The only things in this set, right, so that's this, so there's something in the set that you're equal to, right? So there's some W that lives in here. This is a subset of W, so I can feed it to the coordinate transformation. That's what you're equal to, right, because Y is an element of Rm. Okay, and then, right, W lives in the set, which means that there's a V that W is equal to in terms of T, and then T is representable using A as matrix multiplication of their coordinate vectors. So it's just a lot of layers. It's like an onion. Okay, cool. All right, well, now that we've proven that, we can now get working towards actually demonstrating rank and nullity for general vector spaces. Right, but now that we've got this, let's quickly point out that this immediately tells us something. So if you have a matrix that's representing a linear mapping between vector spaces V and W, where B is a basis for V and H is a basis for W, and V is n-dimensional and W is m-dimensional, then it turns out that the dimension of T of V actually does line up with the rank, and the dimension of the null space does line up with the dimension of the kernel. So there we go. So indeed, those facts are true, and these ones pop out basically for free if you take any basis for T of V. Since the coordinate transformation is linear isomorphism, that means that this set is linearly independent. Hey, remember, we proved that. So that would mean then that the column space of A, which we just proved is the image of T, is the range of T under the coordinate transform. This has to equal the span of A, because that's what we said, it's a basis for that. But then here we go, we have span under a linear image, which means we've got span of the image. So that gives me now that the column space is spanned by A after A has been coordinately transformed. So since this is a linearly independent set that spans, it must be a basis, and these have to have the same number of elements, because again, the coordinate transform is an isomorphism, so it's one-to-one, so guaranteed these are the same elements. So that would mean the rank of the matrix A then, which is the dimension of its column space, is in fact the dimension of the image of this mapping. Nice. And again, really, that just kind of pops out for free because we just demonstrated that the column space of this matrix is the coordinate transform of the range of the linear mapping that A is coming from. Yes. So again, it's not right. This isn't too much heavy lifting, but there is just a lot to keep track of, right? Because we've got a linear mapping from vector space V to vector space W. V has a n-dimensional basis, so this is basically Rn. W has an m-dimensional basis, so this is essentially Rm. So there is a linear map, so there is a matrix that can represent this as matrix multiplication after you do the coordinate transforms. So, right, there's some layers here. Right, so you've got your linear mapping between vector spaces. Those vector spaces can be turned into Rn and Rm, and then the linear mapping can be thought of as a matrix multiplication after those coordinate transforms happen. And here we see, right, rank and nullity do line up with the appropriate defined things for the linear mapping T. And so I proved that for rank, you do the same thing for the dimension of the null space. Right, we know that the null space of the matrix must equal the coordinate transform of the kernel of the mapping, so you do the same thing, take a basis for the kernel, and go from there. Alright, cool. Okay, so with all this machinery in place, we can now prove the rank and nullity theorem for general vector spaces. Basically, the trick is going to be we will convert this over to the exact setting where we can then apply all the stuff we just talked about, where the matrix induced by a linear mapping between vector spaces, basically all of the stuff lines up where you want it to line up. Okay, so the first thing, as I mentioned, we got to take care of some trivial cases, right? Because we're talking about finite dimensional vector spaces, that means we are allowing a dimension of 0, which does not correspond to Rn, so we got to do something about that. So if the dimension of V is in fact 0, then V is the trivial vector space. Since T is linear, it's got to map 0V to 0W, so that means T is just the constant function from 0V to 0W. So its kernel is everything, because everything is mapped to 0, and its range is the trivial vector space. So hey, its range is finite dimensional because it's trivial. The dimension of the domain is 0. 0 is equal to 0 plus 0. The kernel and the range here are both 0-dimensional. So, boom, rank nullity holds if the domain is assumed 0-dimensional. So, we can go ahead and assume that we're actually working with something that has a dimension bigger than 0. So, in other words, it's Rn. So that's nice. Okay, so that takes care of the first trivial case. The next trivial case we need to deal with is what happens when the range is trivial as well. Okay, so we'll get there, but first let's actually set up a basis for V. So, V is an n-dimensional vector space, so it's got n things, it's got a basis. All right, so the first thing we're going to verify is then that the range of T of V is contained in the span of this set. And this is a finite set, so if you're in the span of a finite set, you must be finite dimensional. By Steinitz exchange, any number of linearly independent things that live over here cannot exceed n. Alright, so this is not too bad. Take something in the range. That means you're equal to T of V for some V in there. And hey, we got a basis for V, so we got a linear combo. T is linear. Apply it so that W then is equal to T of V, which is then a linear combo of T of V1 to T of Vn. So W lives in the span there. So there we go. The range of your linear mapping is contained in the span. Nice, so it's got to be finite dimensional. All right, so we got that. So now let's address what I've already talked about, what happens when this is the trivial vector space. Okay. All right, now if it's trivial, that means the range is trivial, which means that T only ever spits out z of w, 0 of w. So that means it is the constant function 0w. So its kernel is everything, because everything gets mapped to 0. So the dimension of the kernel is the dimension of V, but the dimension of T of V is equal to 0. So the formula we're looking for, dimension of the domain, is the dimension of the kernel plus the dimension of the range, holds. All right, so we can go ahead and assume that, yeah, the dimension of the range is actually more than 0. Okay, so in other words then, we've got a linear transform by a change of codomain from V to T of V that are finite dimensional vector spaces, where the dimension here is n and the dimension there is m. So that means we've got access to the matrix representation to this linear mapping after you fix some bases. So fix them. All right. Then what happens? Well, as we proved, for this matrix A, its rank is the dimension of the range. The dimension of its null space is the dimension of the kernel of the linear transform. By rank nullity, we know that these things add up to n, which is in fact the dimension of V, and boom, there we go. The dimension of V is the dimension of its range plus the dimension of its kernel. And there we go, we have now proven rank nullity to be true for any linear mapping from a finite dimensional vector space to an arbitrary vector space. Nice. Okay, so note the trick here was to basically go, well, even though the mapping maps into W, we can change the codomain, and right, then you've got that it's a mapping from a finite dimensional space to another finite dimensional one. There we go. So, cool, there we go. So, indeed, we now have access to rank nullity for arbitrary vector spaces, so long as the domain has dimension n, where n can be any non-negative integer. All right, so now that we've proven that, we'll finish things off, and here we go. We made it. 73 slides. We made it. We did it. We're free of the tyranny of these slides. I want to say, and unfortunately, I do have to say this will not be the last big-ass chunk of slides. When we get to determinants, that's going to be another, it's going to be just like 70 slides. It's going to be another big set. Because kind of determinants are really, it's similar to this. It's not exactly easy to sort of segment that stuff. But anyways, let's now actually prove the following. So a promised result. If you have vector spaces that have the same dimension, they're finite dimensional, and you've got a linear mapping between them, then the mapping is 1-to-1 only if it is onto. Okay, so this is really nice, right? And then sort of I've already said that this was true, and now we can prove it. So yes, so we specifically pointed this out when we had a linear mapping from R2 to R2. We proved that it was 1-to-1, and I said that this also means it's onto, and we'll prove why that's true later. So this is really nice, and this again gives a little bit more credence to my claim that we don't care about onto linear mappings, because right, for us, we're only ever going to care about linear mappings between finite dimensional vector spaces. And in that setting, when the dimensions are equal, then 1-to-1 is in fact equivalent to onto. That's very nice. And it's also worth noting that finite is required here. So as I've noted, you can study infinite dimensional vector spaces. That branch of math is called functional analysis. And this falls apart. This is no longer true, which is mildly annoying, but not the worst thing. All right. So let's prove it. And before I move on, the reason it falls apart is because there is no version of rank nullity for infinite dimensional things. And this completely hinges on rank nullity, so let's see that. So if your mapping is 1-to-1, what do we know? A linear mapping is 1-to-1 if its kernel is trivial. So by the rank nullity theorem, the dimension of V, which is the dimension of W, is equal to the dimension of the range plus the dimension of the kernel. The kernel's dimension is 0. So here we have the dimension of the range is equal to the dimension of the codomain. So that means we know that the mapping is onto. We prove that. All right, and here is a classic, again, example of a proof where once we got the forward direction, the reverse direction is like, oh yeah, just read that backwards. Indeed, if you're onto, what do we know? That means we know the dimension of T of V is equal to the dimension of W. The dimension of V must be the dimension of the range plus the dimension of the kernel by the rank nullity theorem. Okay, this right here is equal to the dimension of W, but by hypothesis, that's the dimension of V. So there we get the dimension of V there. So that minus that then gives me that the dimension of the kernel is 0, and thus the kernel must be trivial. So we have that T is a 1-to-1 mapping. So there we go. 1-to-1 and onto is equivalent for a linear mapping between finite dimensional vector spaces of the same dimension. A fact that is going to be very, very useful for us once we start getting to using all of this great stuff for systems of linear equations. That fact specifically is going to tell us something very important about matrix multiplication. All right, so again, we've kind of been hinting at that the whole reason we built up matrix multiplication was to help us solve linear systems. Matrix multiplication naturally leads to linear transforms, which is what we've been studying now for the better part of 2 weeks. And now that we got all of this stuff under our belt, all these big guns, it's time to go in and actually talk about what do you do to solve systems of linear equations. So we already talked about using Gaussian elimination to handle that, and now we're going to use all of these big theorems to sharpen that process. Okay, cool. So that is the goal for next time, where we'll bring all of this around to actually solve linear systems, and it's going to be great. It's going to be great. You'll love it. It's a way of life. Okay, that is it for the story for today. So, we'll see you next time.